Hi, this is Introduction to Glazes from Alfred University. I am Matt Katz. This is July 7th, 2016. This is Hangout 2 for our summer session of Introduction to Glazes online. Kristen, you missed last week, but generally we just go with questions, sort of what your questions are as to what we've been talking about, questions that you might have that pertain to the future. A lot of the times that the answer is hold on, we'll get there. But I'm more than willing to field any questions that you might have, but especially the things that we've talked about in class so far. So do either of you guys have any questions at this point?
I have a couple of them.
Sure.
Now, one of them probably because it was from one of your lectures. You said to remind you about to explain what makes Gorilla Glass.
Ah, right. Oh, Gorilla Glass is great. Okay. So again, random tangent, and yeah, I tend to do tangents. So Gorilla Glass is super cool, and actually Gorilla Glass becomes really important. It doesn't come up in this lecture. It comes up in Glazes. In this class, it comes up in Glazes too when we talk about glaze durability. And this is a glaze that has. Ooh, I'm getting sunshine on it. Close my window just a little bit more.
Is that the lemon?
Yeah, so this is the test that failed, the lemon test, and you actually saw this one at NCECA, this very tile. So Gorilla Glass is a really simple glass with a really cool procedure. What they do is that they make glass sheets, so it's the same thing that's on your phone, and they make these sheets of glass, and they're fluxed with sodium. Okay, so we started to talk about how we've got these fluxes that are working together, and we've always got our two fluxes. Well, with Gorilla Glass, they very specifically make it with sodium instead of potassium. Then what they do is that they take these sheets of glass and they put them in a bath, a tub of liquid molten potassium. So they take pure potassium and they melt it into a liquid. They keep it heated, and then they pass the glass through it. And what this does is this forces a chemical reaction called ion exchange. Okay, and what ion exchange is literally the sodium and the potassium switch places. Okay, so the sodium comes out and the potassium goes in, and that's this really cool trick because they are inherently interchangeable. Because everything in the column of the periodic table, especially with the fluxes, does exactly the same thing. It does it with greater or lesser effect or power, but it literally plays the same role. And so the potassium or the sodium comes out and the potassium goes in. Well, the potassium is a much, much larger molecule. Okay, it's very, very large compared to sodium. And what that does is that it locks up the physical structure of that glass so that it keeps the or the atoms from shifting and moving and flexing. And although we think of, oh, well, glass is inflexible, it actually is really quite flexible. Glass bends, it just also breaks very easily, and we get into why that happens later. But what happens is by putting the much larger potassium molecule in for the smaller sodium, is it strengthens it just a little bit more, which gives it that durability issue. Why I bring up the lemon test of where this becomes really important is the same reason why glazes fail from a durability standpoint is the same notion of ion exchange. Okay, glazes fail chemically because they are overfluxed for two reasons, really. One, they're overfluxed. Two, they're underfired. Underfired is pretty easy. Fire it to a higher temperature and you'll get greater durability. Overfluxed becomes a real condition, and we'll talk about what overfluxed means later on in the course towards the end, when we talk about how we're using our fluxes and proportions and chemistry and all that. But the short version is, if the glaze is overfluxed, what can happen is that actually something as simple as vinegar or water can induce the ion exchange. And that's because if we think about that first column of the periodic table, the very first element on the top is actually hydrogen. Okay, it actually goes hydrogen, lithium, sodium, potassium. And when we start to talk about this notion of an R2O, you know, lithium is Li2O, sodium is Na2O, potassium is K2O. Well, the first big one is water, which is H2O. And water is a flux. And actually, I had worked on a really cool experiment years ago where we were, when I was still in research, we were working for a kiln element company. And they wanted to see how much we could abuse their kiln elements, their heating elements. And what we did is that we fired them up to temperature. And this was actually really high temperature. This was actually 1600 C. Again, cone 10 is 1300. And we dripped water into the hot kiln, and that vaporized the water and made it an active flux, and that H2O started fluxing out these kiln elements and eating away at them. It was a really, really cool experiment. So anyway, going back to acids, okay, acids tend to be materials that are based in, or they generally are materials that are based in hydrogen. Hydrochloric acid is HCl, hydrofluoric acid is HF. Well, that material is very chemically active. So if you take an acid, even something as simple as acetic acid, which or citric acid, which is in a lemon, that hydrogen is chemically available. And if your glass is weak, the hydrogen will switch places with whatever excess amount of flux you have in this glaze, which is what causes the lemon test failure. Okay, is having too much flux. Now, what is too much flux? We'll get to that. That's a bigger discussion that we get to down the road. But yeah, so actually the same thing that makes Gorilla Glass strong makes glazes, we'll say, weak. You know, the whole notion of food safety, I don't really like that term. I really don't talk about food safety per se, because it's both overused and understood. Understood. What's a better way to say that? But it's not a great term or concept. So anyway, so that's Gorilla Glass. It's really, really amazing stuff, and this whole property of ion exchange is super cool. Good question. Sorry, did I talk too much?
No. Is there a reason that they swap out? Like I think you said, was it sodium and potassium?
Mm-hmm. By swapping them out, it just makes that glass super strong. Kristen's heard this, but the way I describe the reverse ion exchange for making a glaze weak is, imagine a brick wall, right? And pull a brick out of that brick wall, okay, and put in a Lego brick, okay. So you take out a full-size brick and you put in a tiny brick. Okay, and then just keep doing that. Just keep taking bricks out of that brick wall and replace them with Lego bricks. Eventually, the brick wall will collapse because the tiny brick does not fulfill the physical needs of the larger brick. For the Gorilla Glass, it's the opposite. Take out a brick and then insert a brick that perfectly fits all the negative space. So the grout and the mortar and the intricacies of the bricks that it borders and all that. So it perfectly fits that shape, and it just makes that brick wall super, super strong. It makes it like a cast concrete wall, but even stronger because the material is tougher and doesn't break down. So it's just one of those neat tricks of chemistry.
Okay, that makes sense, because I was gonna say it can't be like random that happens.
Nope, it's just that cool trick about that first column of the periodic table. The fact that that the first column of the periodic table, since they all have this +1 structure, right? So hold on, let me pull up my periodic table here. Share my screen. Okay, you're gonna do this to me. Hold on one second. Reduce my resolution, increase my resolution. I'm just going to pull up a periodic table. Okay, so because that first column of the periodic table right? Lithium, sodium, potassium, rubidium, cesium, francium. Because they all have that +1 valence, because they all need an electron to bond, they can be substituted for each other in the glaze. And this becomes really, really important as we go forward. The same thing with the second column, magnesium, calcium, strontium, barium, and then zinc comes up as well, that because they have the same atomic structure, we can use them interchangeably, and they still do basically the same thing. And it becomes a really, really neat trick that we can do. Well, it's not a trick, it's just the way that the system functions, because different fluxes give us different results. The first one off the top is that lithium, sodium, and potassium inherently have different melting temperatures. Since lithium is a very small molecule, it melts at a lower temperature than sodium, which melts at a lower temperature than potassium. It also gives us different results as far as color and texture, but again, that's a bigger conversation from down the road. Okay? So again, it's one of those neat little flukes of chemistry that we get to take advantage of. Do you have another question?
I think I had a couple more. I just had to find them.
I have a tiny question.
Go for it.
Do you know off the top of your head the formula for acetic acid, just for my edification?
I don't, but Google is your friend.
Yeah, right? Like, why didn't I do that?
Acetic acid. CH3COOH. Is that right? Yeah. C2H4O2. I know. I have a lot of random things memorized, but not all of them.
Random stuff is cool.
Yeah, right.
Thank you.
So, did you have another question?
Yeah, this one was just about how in trying to think of how to word it. In your lectures, just the way that like some things are like formatted, I guess. Like when you were talking about kaolin and it's Al2O3, and then I don't know. I guess instead of like a plus sign or something, like there's the symbol there that's just like the dot. Do you know why that one is used, or do you just use it? Because at first it was confusing me. Like I thought it was like supposed to be a multiplication symbol or something, but it seems more like addition.
No, that's just chemistry notation. It's a great question. Actually, I just learned that in chemistry, and I don't know why we particularly use that. If there's different ways of writing notation in chemistry. Sometimes, like I just posted in the chat, the formula for acetic acid, and sometimes you'll find where they just mash everything together into one big formula. For kaolin and for a lot of our materials, it's actually important to separate them out into their individual components, because they actually sort of do remain their individual components, especially clay. Okay. Let me see. Today's lecture. Wait, hold on. Let me pull up today's lecture. Right, where we start to talk. Okay, yeah, we did. So in today's lecture, we talk about the nature of kaolin. Okay. Let me do a screen share. Okay, oops. Before I freak you all out. Okay, so in this notion of kaolinite, okay, can you guys see the kaolin image?
Mm-hmm.
Okay, kaolin, okay, has a specific structure that actually reflects the nature of silica and alumina. Okay, so silica is SiO2, and if we look here at the actual breakdown, you'll see that this is a silica, the black dot, and then 2 oxygens. Okay, and then a silica and 2 oxygens, and it gets a little bit more complex because it's actually sharing oxygens between multiple molecules, excuse me. But anyway, so we've got SiO2, and that is literally one side of the clay particle. Okay, whereas the opposing side is alumina, which is Al2O3. So technically you have 2 aluminas and then 3 oxygens, makes up 1 alumina molecule, and that is the opposite side of a kaolin particle. Okay, so and then they're bonded by having extra hydrogens and oxygens in there, which come in the form of chemically bound water. So this is really important because each one of these materials has a different surface charge. Okay, the silica surface is negative and the alumina surface is positive. And that's important because that makes our clay into these little magnets, which is the whole reason why clay works as we know it, that it sticks together and you can shape it at room temperature because all those little particles are for basically little magnets that stick together. So representing it as such, as there's a silica part and an alumina part, is important to the notion of the chemistry of clay. So breaking it down becomes a little bit unnecessary, and so really just keeping it with the dots and separated is just sort of chemical notation.
Okay.
Good question. Do you have another?
Yeah, I think it had something to do with alumina actually, so I just have to read through it to remember what it was a little bit longer, I think.
I have another quick one that might be irrelevant. Is that okay?
No such thing as an irrelevant question.
All right, well, just what temperature-ish does sintering happen?
Interesting question that again the specifics will come up later. That's complicated.
Okay.
The process of sintering really sort of happens over a range of temperatures. Okay, for a clay body, it really depends on what are the components of the clay body. But generally, actually, sintering is really taking place just a few cones under bisque temperature. And so, generically, most people will bisque porcelain to cone 04, they'll bisque stoneware to cone 08. We tend to do it at those temperatures because that is where we've gotten to a point where the material sinters. So say if you soak it in water, the bisqueware in water, it doesn't dissolve. But if you fire it maybe 2 cones, 4 cones under that, and you put it in water, it's very easy to scratch and scrape, and literally it will begin to dissolve. But it's always specifically revolved around the temperature of the materials in that particular formula. So, if bisque temperature cone 04 is basically 1950 F, 1070 C, probably around 1000 C. And there are plenty of things that happen in the firing underneath that, but the actual sintering is really right beneath bisque, and bisque is a very sensitive temperature because we want to get the material fired to a point where we are sintered, but we haven't begun to melt at all, and we haven't begun to reduce our pore size, because if we reduce our pores, getting towards vitrification, then we don't have a bisqueware that absorbs glaze or absorbs the liquid in the glaze, so the glaze doesn't stick, which is the classic that we've all seen, that if you try to apply glaze to fully fired ware, it doesn't stick because there are no pores.
Yeah. Okay. Thank you.
Sure. Sylvia, you got your next one?
Yeah. I think it was just something that I don't know, maybe I'm not understanding it right, but
That's why we're here.
in one of the readings it said the only glazes which are commonly made without alumina are those which are intended to develop crystals during cooling. And I thought that was for like matte glazes, but then it says because of its high melting point, alumina lends opacity and matteness to any glaze if it is used in amounts beyond a certain critical limit, dependent on glaze composition and the firing temperature.
So again, this is partially true and partially why I'm not crazy about some of the readings, because even the ones I like have questionable application of information. Okay, so the first part, alumina in crystalline glazes. Okay, this is specifically starburst crystals, right? Try to get away from the reflection. Sort of starburst crystals. Oh, where's my big one? Okay, what we traditionally think of as, crystalline glazes. These glazes tend to be very low alumina. We'll get into why they're low alumina when we get to special effect glazes. It's believed that alumina will restrict the growth of this type of crystal. Okay, this is not a matte glaze. This is a gloss glaze that has a particular chemical special effect that grows crystals. And again, we'll get into the subtlety of it. It's not that alumina restricts the growth of crystals. It's just that if you add alumina into this formula, it grows a different type of crystal, literally a different molecular structured crystal. In a matte glaze, though, again, this doesn't show real well. This is a well-composed matte glaze, and what this is that this is a glossy glaze that crystals grow in, and that's because of the chemistry of this formula. And what this is the glaze actually does have excess alumina. Okay, in what would be the glass. So in chemistry, in these reactions, we're trying to form stability. Okay, and the problem that we have is that if there's excess anything in our glass, okay, it can't just hang out. It can't just sort of force itself, it becomes like the fifth wheel on a double date. It's that guy that you got to get rid of. So you got to find him a date. Well, what our glazes do is that they will bond with other materials that are hanging around. So if you have what would be excess alumina for a stable glass, that alumina will then partner with some calcium and some silica to precipitate crystals. Okay, so that's what it's talking about. It's really talking about two different types of glazes and different uses of alumina. I guess I'm not crazy about sort of talking about the crystalline glazes right now, because this sort of comes up specifically as, I'm not focusing, as a special effect. Okay, whereas matte glazes, just straight up matte glazes, are basically a normal glaze, a glossy glaze that crystals grow in homogeneously, okay, so evenly, consistently across the entire surface, which is the big important detail, right? This is sort of random and specialized. This is homogenized. The entire glaze surface is crystallized, and that's a really important detail for a matte glaze versus a special effect glaze. Does that answer the question? I don't know if I answered that.
Yeah, I think so. So basically, like the first section I read was like their wording was just a little bit weird because it doesn't mean like alumina. It's just talking about different kinds of crystals.
Yeah, exactly. They're completely different kinds of crystals. And again, as we go forward, we'll get into exactly what the chemical composition of the different types of crystals are. But you use different conditions to form different types of crystals. So different chemistry, different raw materials, and different firings to get different types of crystals. Good question. Oh. Did you have another one?
I think that's all I had from like the lectures and readings and stuff.
Okay. Kristen, did you have any more questions?
I don't really think so. At one point, I think I was a little confused by like mag carb versus mag oxide, and I think I've resolved that in my head. It's like you're using it for the magnesium for like its fluxing property, right? And then you just have to figure out how much oxygen you have and how that factors into everything also.
Well, yes. It's always just about when we're looking at any of our materials, and this is really where we're going for the next couple of lectures. It really comes down to understanding why we are using a particular material. Okay, and specifically, so if we go back to the sort of the generic nature of a glaze, we have these 4 types of materials that we need to represent to make a good glaze. Okay, there's our alkaline metal flux, there's our alkaline earth flux, there is silica, and there is alumina. Okay, and we happen to use 4 types of material on top of it. We happen to use feldspar. We use the carbonates, the alkaline earth carbonates, we use clay, and we use flint. Well, amazingly enough, shockingly enough, that those 4 types of materials each represent one of the 4 chemical constituents that we need. Okay, so feldspar represents alkaline metal, the carbonates represent alkaline earth, the clay actually represents alumina, and then the silica, flint represents the silica. So, as to why you pick a particular material, okay, we need to look at the 2 conditions of how we're using our materials. One, does it work in the firing? Okay, does it give us the chemical constituents we need to get the fired composition that we want? And that is that's where we're going with building all of this chemistry and understanding materials. But the second condition that we must be worried about is, does it work in the studio? Okay, can we mix this into a glaze? And mag carb becomes a real problem. Okay, now magnesium carbonate should be a wonderful material. Okay, it's literally just magnesium oxide and carbon dioxide. Well, the carbon gets driven off as a gas, and so we don't have to worry about it. But it has, and we use all sorts of carbonates. We use, whiting is calcium carbonate. Again, calcium oxide and carbon dioxide. We use strontium carbonate, strontium oxide and carbon dioxide, and barium carbonate, or barium oxide and carbon dioxide. And literally, when you fire it, the carbon dioxide gets driven off as a gas, and it just goes away. We never have to deal with it, and we get left with the oxide that we want. Mag carb, though, has a studio problem, which is that it is very, very fluffy. And so it's impossible to mix into your glaze. It's not impossible, you can do it. But we have alternatives. So we can look at a material like talc, and this comes up, it's not in today's lecture, this comes up I think the next lecture, if not the one after that. But talc is a fairly acceptable material. Now, talc chemically is different. It's magnesium and silica. Well, that puts us at a slight disadvantage because now we're bringing in even more silica. And if you remember, our feldspar has silica, our clay has silica, our silica has silica, and now we're bringing in an alkaline earth, which traditionally is the one material that doesn't have any silica in it, and we're bringing in silica. Now, can we compensate for that in our formula? Take maybe some silica away, use less flint? Absolutely. That's one of the cool tricks about chemistry. But it's sort of something that we now have to consider. We now need to look at, because again, if we don't balance our molecules perfectly, we don't get the result that we want. That's just the basics of chemistry. So now, if we're going to use talc instead of mag carb, we have to think about why we're using it and what is this extra thing that it introduces. Okay, and we have a similar material for calcium. There's a material called wollastonite, which is calcium and silica. Some people use wollastonite in glazes. I don't. We could talk about why later. But again, the primary reason is it's bringing in silica that I don't want to deal with if I don't have to. And calcium carbonate's not fluffy, so it goes straight into the glaze, mixes up super easy. Okay, so we don't have any problems with it that way. So, you know, why we pick which materials, and again, this is why the next 3 lectures are literally like listing all the materials that we use, because you need to know. Okay, it's the totally boring memorization part, but if you walk into a glaze lab, you need to know what's this feldspar, what's that clay, what's this alkaline earth source, because if you don't, you just go back to shooting in the dark.
No, this is like so useful, but I really have, like you say, noticed people be very afraid of digging into it in like a considered way. So yeah, where I have been avoiding doing my glazing at, they have downstairs just whole bins of materials that I think they're going to let me screw around with, which is great.
Great. And there's no reason not to. It's just you have to understand what it is. And I remember the first time when I was an undergrad, and yeah, I walked into the glaze lab and there's all these bins of stuff, and you're like, well, what's all this stuff? And no one's telling you. And, you know, maybe you go and find a glaze formula. You know, now you can go online. Back then, there was SDSU. There weren't really that many online glaze resources. But you'd go to a book, you'd pull up a formula, some grad student gives you a formula, and, you know, it just, here's your list of materials, and you go and you just make what's there. Well, that's okay, but it's no way to learn. It's no way to understand what's really there. And, you know, that the other confusing thing is that a lot of people use brand names. Brand names is super important because, you know, maybe you know that you've got, well, last night, but maybe you've only got somebody labeled Vansil 20 on the bin, and, you know, what do I know what Vansil 20 is? But that's brand name. And, you know, I think it's important to develop relationships with our materials to know what this is going to do, what it's not going to do, and again, to sort of not sort of give in to, again, honestly, what people tell you. I mean, obviously believe what I tell you, because, you know, I theoretically know what I'm talking about, at least that's why I'm here, but, you know, that there's so much myth and conjecture and speculation, and I heard from a guy, and the wise old potter told me, and that's, you know, it's all old wives' tales. You know, oh, use this, don't use that. You know, I was talking with I'm teaching my Glazes 2 course right now, and so we have our hangouts on Tuesday night. And I was talking with my students last night, and then you know, they were talking about one of them was talking about coming across high temperature glaze formulas that use lithium carbonate in the formula, and I'm just sort of like pulling my hair out, because any sensible person would never put lithium carbonate in a high temperature formula. There's no use for it and no benefit. And like this glaze had a major amount of it, and it's like, and you know, I always get this question of, oh, well, why did this person do this with the glaze that I've got? And my answer is always, I have no idea. Don't ask me, because most of the people that are working in glazes in companies that are selling glazes have no idea what they're doing as far as chemistry. You know, the story I always tell is that the company that my wife used to work for, which was a tile company, selling a lot of tile, their glaze formulas were literally the RISD, the Rhode Island School of Design undergrad glaze book that literally every undergrad copied. And this company was selling, you know, 500,000 square feet of tile every year with these garbage formulas. And when Guernsey Borate went away, they didn't know what to do about it. And, you know, when their formulas didn't work, they didn't know why, because they literally had made they're in their 40s and had made this career on this glaze formulas that they literally did not know why they worked. And it's disappointing to me more than anything. And I get worked up about stuff, so I should shut up. Did you have another question?
I really don't.
That's okay. So don't worry, I won't hold you hostage. Everybody can go free. So just keep plugging away. Now, next, the one thing I will say is that technically next Wednesday would be the midterm. I think I'm going to put it off until next Friday. So you'll have a few days to review before we actually do it. I don't care. Well, I mean, I do care about the midterm, but it's open book, open mouth. If you want to hang out with other students, put something on the message board and say, hey, do you guys want to get together on Google Hangouts on, Saturday morning and do it? I don't care. It's up for like 24 hours at least, if not longer. I forget. It's pretty easy. And again, we can talk about that more next week because I'll put it up next Friday. The next two lectures are just all going to be materials all the time. And then after we get through materials, after we get past the midterm, and I know you're like, hey, we've only been here a week and a half, and you're already talking midterm, but that's the way summer session works. It's just fast and furious. Then we get into the serious fun. And I often say, like, the first 6 classes are sort of a slog. You got to get through chemistry and geology and learning about all the materials. And then when we get to the other side, like, it is where, like, the really, really fantastic stuff comes up. Really getting into glaze chemistry, manipulating glazes, understanding really how they're working, how temperature works, all this great stuff, like how cones work, all this really fantastic stuff. So it's going to be a lot of fun. Just have to keep plugging away. Anything else?
Well, I wanted to say that thing about underfiring glazes, turning them into matte glazes, I've like totally observed that, so that cleared up some stuff. So that was very satisfying.
It's a serious problem.
And the studio that I work at, like, now they fire at cone 6, but really she fires to cone 5 for her glazes, and it makes me, like, again, not want to use glazes. It's very frustrating.
Well, I think, and again, you can call me a crazy person, but like I know what I'm talking about. The way that cone 6 has been implemented has become a problem, or it inherently is a problem. That there were a bunch of people, and it sort of came around. I ask a lot of older people who were around for it, but it seems like somewhere between the 60s and 70s that this transition came around, and basically a lot of people, for either environmental reasons or budget reasons, decided to go through this major development transition, and not a lick of them knew anything about the actual glaze chemistry. So they're literally just shooting in the dark. And so, that you hit these problems, and something, again, that I really get into this in glazes too, but actually this pot I keep showing, this is just a pride and joy of mine. Actually, that's the bottom of the pot. This is the whole pot. That this is from a grad student of mine named Kelly Justice, and she happens to be one of my favorite potters. But this was a condition where she had come to me with this glaze formula, and she loved it. It was literally, she said, this glaze is always glossy when it's fired hotter. She's like, I've got this matte glaze, I love the color, but if I fire it a little bit hotter, it's glossy. And I'm like, no, that's a terrible glaze, because a matte glaze is always going to be matte. That is chemistry. And if it gets glossier when it gets fired hotter, that means that the firing is incomplete. That means you're just underfired. And so we were able to take her glaze and reformulate it and make this beautiful, true matte glaze, and it's absolutely lovely, and I love what she did with it at cone 6. And here's another pot of her. See my family's passports, but this is the same glaze, and you can see the gloss reflecting off the surface. These two are essentially the same glaze, like this beautiful buttery matte in this high gloss, both at cone 6. They have different colorants and slight tweaks to their chemistry, but incredibly rich texture, rich color, solid food safety in the chemistry, and it's simple tweaks of just understanding your materials. But yeah, anybody who, I fired a little bit hotter, I get it more matte, less matte, whatever. There's no such thing. You want more matte or less matte? That's in the chemistry. It's not in the firing. And yeah, it's 6 is such a problem. I mean, you'll hear I rant on and on and on about it. I know it might make people frustrated, but it's a real problem, because again, that you pick up books. There's a book that one of my advanced students is currently dealing with a glaze from a well-known mid-temperature glaze book.
Is it like a recent publication that everybody thinks is really great? I think I know what you're talking about.
Yep. And
I was going to ask you about that guy.
that this glaze is published, and the glaze is not durable. It's not fully fired. It's not a good glaze. And this student of mine asked the author about it, and his defense is, hey, it's not my glaze. I just published it in my book. What? Like, no, that's not acceptable. And so she's gone back to re-engineering it and has done great stuff. But yeah, there's very popular books out there with a lot of formulas, and anybody can publish a book. Literally, you just need to put words in a Word document and get a publisher who will put it on a piece of paper. That's all it takes to get a book out there. And yeah, they get a reputation for being fantastic, and it is what it is. So the great thing is by the time we're through this, you'll know who to trust, because you're going to be the person who to trust, because you're going to know. It'll also make you terrified when you go back out into the world and see what other people are doing, and you're going to go, oh my God, you're all doing things wrong. This one student of mine, Sue, this is the problem that she had. She was one of my first online students, and she got through the course, and then she went back to her program, and she was like, oh my God, you guys are all like a disaster. And now she's spent a year and a half trying to fix it, and she's diligently plugging away and doing great things. So you will be the authority by the time we get to the end. So have no fear.
Okay, I have one more thing.
Okay.
If that's okay.
Yeah,
Just like a quick thing. So I am obviously intrigued by like crystalline glazes because they're beautiful, and so have looked into like the slow cooling stuff that seems to be necessary according to people, and people also say that like slow cooling is good for iron glazes and so on. And you mentioned that you would talk about how crystals can grow at like normal cooling or something like that, just because of their chemical formulation. It doesn't have to do with the cooling. So I'd be interested in like learning more about all that at some point. I don't know if that's going to come up or if now is the appropriate time to talk about it or what.
Some of it comes up in this class. Some of it comes up in glazes too. But the short version is the crystals will grow, okay, in a crystalline glaze. You don't have to have you don't have to have the soak. Now, if you want, again, if you want, these are fairly large crystals, okay, they're 2-3 inches in diameter. To get them large, yes, you have to soak. Okay, the longer you soak this, the bigger the crystals get. Okay, but those glazes will grow crystals just on a natural cool. They're smaller, but they will grow. Actually, this is really important as to the last topic, because crystals have to grow in a glossy glaze, in a gloss. Okay, and so true matte glazes versus false matte glazes, which are just under fired. True matte glazes, if you open up that kiln at temperature, they look like a glossy glaze. You literally cannot tell the difference between the gloss glaze and the matte glaze, because on the cooling, the crystals will precipitate. Now, you can slow your cooling. You can fire down. You can do all sorts of things to keep the time growing crystals longer, and that will change the intensity of the crystals or the size of the crystals. That is a fact. Now, for matte glazes, it's really not that much of a benefit, because matte glazes, because of the stability of the chemistry, they'll just precipitate, and since they're homogeneous, they just grow all over the place. In fact, slow cooling for a matte glaze can be a problem, because matte glazes, true matte glazes, can run. Okay, I forgot to turn on my overhead light. But here, like, okay, you can't really see it, but this is a matte glaze. Like, I can't get any reflection off the main tile, but you'll notice I've got a little running rivulet down here, and that's because this was a glossy glaze. Well, a glossy glaze is fully melted and can run. And a matte glaze can run too, because the viscosity of the underlying glass is low. Okay, means it thins out at temperature, and the gloss part runs, but the crystals sort of form a network, like an armor, and they sort of stay in place, but the underlying glass sort of just slips out underneath. So a true matte glaze can absolutely run. a false matte glaze, it won't run because it's not turned into glass. So the more time that you soak, the more crystals that you'll grow, but also the more likely you are to make running happen. So again, it's an aesthetic trade-off. For some people will slow cool their normal firings. I mean, if you want to knock yourself out, I think you're mostly just burning gas. But every now and then I run into some person that's absolutely got some reason why they do things, and they might have a particular result. And okay, I mean, I'm not going to stop you.
Yeah, I've heard that like solves pinholing and other.
No.
Okay.
Nope. We'll get into pinholing at the end. And actually, that's funny. Again, sort of going back to Sue in Glazes 2 right now. She's actually doing an in-depth study on pinholing. So we're actually going to know a lot more at the end of this term. But right now, I am 90% sure that everything that is taught about pinholing is bunk. I have a friend, Dave Finklenberg, who is a potter but did his master's thesis in ceramic engineering and studied pinholes. And his thesis is pretty rock solid, and there's very little reason to believe that pinholes are caused by gas release or this or that, or that slow cooling can heal them. Slow cooling could just as easily expose them. And again, we'll get into the nature of where pinholes come from and how they work and all that. But yeah, no, it's mostly just pinholing is mostly an application issue more than anything.
Huh.
But we'll get there. That comes up towards the end.
Okay. All right. Well, thank you. I'm very excited.
Cool beans. Okay, I'm going to stop the recording. Hold on for 1 second. Okay.